there for the introduction, and I will share my screen. It's so nice to see at least familiar names up on the screen. I can almost see you there behind your... let's see, you can't see my my thumbnail video now, right? Only the screen, I hope.
I can just see the screen.
Yeah, good. Right. Okay, excellent. I have a little thumbnail video indicating who's talking at the top. All right. Sorry. Here we go. Great. As Claire said, the topic of this colloquium is stellar spectroscopy, and it will be a shameful advertisement for the GALAH survey in particular. And the reason is that it very nicely times with the third data release of the GALAH survey, which is happening in 3 hours. It's then 6 o'clock in the morning in Australia, and this survey is, of course, a mainly Australian-led survey. It's been running for many years on the 4-meter Anglo-Australian telescope in Siding Spring, and you can see this little widget here on the right, how many stars or where the stars are located. This animation is now a little bit old, but you can see that we are casting beams out into far out places in the galaxy, although it is primarily a local survey. So what will happen then in 3 hours is that we're not quite entering the million star spectroscopic era, but almost. There will be for 600,000 stars or 700,000 spectra. There will be stellar parameters, up to 30 individual chemical abundances, and reduced spectra as well, of course, and a lot of other data, like radio velocities, for example. And you will be able to go on to, this link here, Docs Data Central GALAH, to download them for yourself and inspect all these data. And it will also be, of course, accompanied by a data release paper and several other papers that will be put on the archive tomorrow. And I will mention some of them during this talk. Australia was not in the resume that Claire read up, and I never been there, but we were lucky to form a German node of the GALAH survey for many years. So before I left MPIA, we had a small team there, and it's all credit to them, really, especially to Sven Buder, who is the lead author of the second and third data release of the GALAH survey. So I moved to Stockholm a year ago, and they all dispersed. Sven is now a postdoc in Australia at the ANU there. But everyone that you see here were involved in the survey one way or the other. So here's the survey footprint of all these 600,000 stars that were observed in phase 1 of the survey. This is these observations were then taken 2014 to 2018 over 300 nights on the AT. GALAH has already entered into phase 2, but that is not part of the third release. As you can see here that it's mainly in the main survey in blue here, we are avoiding the disk midplane due to crowding, but we still want enough stars to fill our fibers. There's 400 of them, so we are avoiding too high latitudes as well. And in addition to this main survey, there are footprints covering the K2 fields and the test fields, so that we can acquire spectroscopic data for stars that also have seismic information. So you can get really excellent ages for those stars. And as said, it's mainly a bright survey. So this is the nominal range of the main survey is about 9 to 14, and some extensions to the fainter end. Then you might ask, well, isn't Gaia already observed? Hasn't Gaia already observed all these stars? Yes, but Gaia, they're faint enough that Gaia is only delivering, well, not only, but it is delivering the 5D phase space, so the position, parallax, and proper motion for the stars, while the radio velocities, to obtain accurate radio velocities, we need to obtain a ground-based spectrum. And GALAH is doing so, and it's of course also adding the ages and chemical abundances. And I will not talk about radio velocities at all. I'm just showing you this picture to demonstrate that we are doing what we are supposed to in terms of radio velocities, in the sense that GALAH, the GALAH precision is better than what Gaia can deliver for stars in the magnitude 9 to 14, which is the main range. So I will soon launch this little video here, and you'll see the star moving along the HR diagram, covering all the different stellar types that the GALAH survey is covering. So this is an FGK type survey, and you will see how the spectra change appearance, and I hope that you will appreciate the challenge here in analyzing all these very, very different spectra in a homogeneous way. So we have here the 4 bands of the HERMES spectrograph. It's a blue band around H beta, a green one in the middle, and then we have a red band around H alpha, and the near infrared band centered on the oxygen triplet. And those wavelength regions were selected to cover as many lines of different chemical elements, of different nucleosynthesis channels as possible. Right, so sorry, I launched this. So you see, especially as you're coming from the cool end, there's almost no continuum left in those spectra, while at the turn-off they look very nice and well behaved. So, and obviously having 600,000 of them and wanting to extract so much information is extremely challenging for the analysis methods. But before going into details, I just want to summarize. Of course, the main science that is done with GALAH is understanding the galactic disk. It's mainly a field survey, and it's predominantly covering disk stars. However, there's about a 5% component there's a 5% fraction of a halo stars in there as well, at least if you judge that kinematically. There are some clusters, both open and globular as well, and there's some science papers on that. And the main science cases you see here to the right. We want to understand stellar evolution, galactic evolution, and this elusive concept, chemical tagging, meaning that by analyzing a star's chemical abundance pattern, we want to connect stars to each other and to, ideally, to a common birth origin, either a common birth cluster or a common birth location in the galactic disk. And if you would go to the archive now and look for GALAH survey papers that have been published, you would find a list of 30 or so coming out from the consortium, and you see most of them have been published over the last couple of years only, and the majority of them following the second data release. But if you make some more room on the slide, if you repeat the exercise tomorrow, you will see those papers as well, and especially, as I said, the third data release paper. And for the remaining of this talk, I'll talk about those ones marked here in red, which are the papers that me and my group were most involved with. So if we start with the second and third data release and compare the data, you can see here how the HR diagrams of the releases have evolved, going from 10,000 to 350,000 to 650, or yeah, varying numbers and varying renditions of these figures. Yeah, you can see that especially between DR2 and DR3, the morphology of these these sequences change, and that has to do with just simply the way we analyze the stars. We determine different stellar parameters for them, and we hope we're going in the right direction. And so for the first two releases, we used a traditional spectrum synthesis code that is optimizing parameters by chi-square minimization between observed and synthetic spectra. So it's synthesizing the spectrum on the fly. And this was done for about 10,000 stars or so, that then formed a training set. And then the so-called labels, so the parameters and abundances for the entire training set was determined by label propagation. So these machine learning codes like the Canon, there are many others, they learn from how each individual pixel is varying as a smooth function of the different parameters that we want to determine. If you build a model on that based on a training set, you can then propagate the information to the full set and simply with algebra. And the computational cost for that exercise is quite small. The Canon itself can probably run on a laptop, even for so many stars. But while SME is quite costly. However, for DR3, we decided to tackle the entire data set with SME, simply because this was the most, well, there were two reasons. This is the most straightforward way we could envision to make use of the really excellent astrometric information we had for all the targets. So we've been using the Gaia data and the typically 3% error in parallax to put an additional constraint on the surface gravity whilst iterating the stellar parameters spectroscopically. And that has really made a huge difference. You can see that the main sequence actually looking like a main sequence, doesn't have any fiducial upturns or downturns. And there's the red clump is horizontal rather than vertical as in DR2. And this is all thanks to Gaia. However, it came at a cost of computational cost. It's of the order of 1.2 million CPU hours spent on this analysis all in all. It's about 2 hours per star. And just to show you what we do for abundance measurements, as I said, because each individual line that we wanted to extract an abundance based on has a different blending proportion in different spectrum. So we first compute a spectrum containing only the element of the line, only the element that we're interested in here, calcium. So we compute the red spectrum, and then we compute the blue spectrum containing all the blends. Here, this one has a strong nickel blend. We compare those two spectra and make sure to limit the masks to region where the difference between them is small. And then only thereafter, the calcium abundance is determined by optimizing the abundance in this mask. And this is then done 30 million times. So if you look at the abundances, in comparing again DR2 to DR3, you can see that here you have the alpha to iron ratio as a function of metallicity. Typical, you can see the split in the alpha plane, a thin disk and a so-called thick disk or a high alpha sequence, and extending down to lower metallicities. Here are also the lithium measurements, which are very few actually, that were unflagged in DR2, only a few thousand. All the light blue points here were flagged as unreliable. You compare this to DR3, you can see that at first glance the alpha plane does look more scattered. This is partly, of course, we have more stars, so more outliers are expected, but it's also the case that with a sort of more traditional technique, you are limited by the, I can put this up, you're limited only by the restriction of your model atmosphere grid, not by the you're not restricted by the training set. So it's not that machine learning technique does not have these outliers, just that we can't, they have to be flagged as unreliable because they're far away from your training set. So we wanted to make sure that we were unbiased in this respect with this data release. And also you can see that the number of lithium abundances greatly increased. We have about 150,000 of them, and I will return to that later. So there are advantages and disadvantages with these two different approaches. And I will not I will not go into details about all these different chemical abundances and their patterns. I'm just showing them to you here to prove to you that we have in fact derived up to 30 chemical abundances. And if you are good at math, you're computing that there are 32 panels here, but there are 2 for titanium and there's 1 for alpha. So in the end, there's 30 plus iron. And we have not visually inspected all of these measurements. So there is a chance that this rubidium measurement in a star that appears elevated could be a false measurement. It could be due to a telluric line that wasn't subtracted properly, but we have done our best to make sure we have those things under control as best as we can. Yeah, that's also a reminder to you. We are releasing the spectra. So if you find things that you are not 100% confident in, then go and inspect them. All right, so moving on, I'd like to move to this paper here, this paper that recently came out on the non-LT departure coefficients that were used for the analysis. Just a brief recap here why we think we need a non-LT analysis. We're actually very proud that we have been able to conduct non-LT analysis for the GALAH, for the full GALAH survey up for 12 elements, which is more than any of the contemporary surveys have been successful at. So yeah, sorry, this was meant to illustrate just why we think we need it. As you move outwards in a star out through the atmosphere, the density of course decreases, and the collisional rates, the transition rates of excitation and ionization between different atomic levels, they decrease along with the density, and they become comparable to the corresponding radiative rates. And that means you end up with a non-LT situation, and that transition happens at some point during the photosphere. It could be severe. It could be severely affecting your line profiles, or only or not at all. But you have to do the calculations to know this. So how do we calculate the number? The NIs here, those are the level populations of different atomic species when we can't trust the local thermodynamic equilibrium to apply. Well, we set up the statistical equilibrium instead. So we form the total probability that a certain excitation or ionization event takes place as the sum of collisional and radiative. And then the statistical equilibrium is simply saying that the influx to a level is equals the outflow, and that is steady in time. The numerical complexity then comes in, of course, because the radiative rates depend on the non-local radiation field. So we have to iterate the equations of statistical equilibrium along with the equation of radiative transfer. But the trick is that we can do this, excuse me, that we can do this, we can pre-compute that, and I'll get back to that in the next slide. Here, I would just like to illustrate a non-LT effect, and this is a model atom for sodium here, which I'm using to do that. So if you can imagine that you are in some line-forming region in the stellar atmosphere, then your radiation field, the average radiation field J nu, the red curve here, heavily smoothed, that deviates from the Planck function, and it does so by being in excess at shorter wavelengths. And that tends to boost ionization. So levels that have photoionization thresholds in this region here, they like this level, these two levels here, they become more ionized than the LTE assumption would predict. And the opposite effect is true for levels that are close to the continuum. So you get over-ionization and over-recombination. And of course, in each of the line transitions here, each of the bound-bound transitions, you have similar effects. So the whole model atom here needs to find a to find an equilibrium where the levels are steady. But as I said, all these numerically demanding calculations can be done beforehand, and that is exactly what was published in Amarsi et al. A large grid of pre-computed so-called departure coefficients, and that's the ratio between the non-LTE and LTE level population. And that means that when we're running GALAH analysis, we can compute non-LTE synthesis on the fly with SME at no additional cost with respect to LTE. So that is not why SME is taking long, because we can simply we compute LTE level populations as usual, and then we simply multiply with these pre-computed ratios. And that gives us non-LTE line profiles like these. It's just an illustration that it actually works, giving us these deep line cores in non-LTE. It's a picture that Thomas Nordlander has produced. So that was 1D non-LTE, which we're able to do then for the GALAH survey. It's not the ultimate goal. We are trying to pushing the field to move towards the use of 3D hydrodynamical model atmospheres and combine that with non-LTE radiative transfer. So the ultimate goal here is, realistic modeling of the convection that happens at stellar surface, the radiation, and the statistical equilibrium of atoms, and all of this ideally without a lot of free parameters. And it's not that it can't be done; it can be done. We have proved that we can do this also for very complex species like iron, which has a model atom that you can see here. It's horrendous. It has 500,000 transition at least. But it's too numerically demanding, and we can only produce synthetic spectra for either for a handful of stars or a handful of lines in many stars. So we're not yet there in terms of survey production. Then you might ask, why do we choose if we are here now, or the field has been here in the 1D LTE regime for decades, and we want to move here, 3D and LTE. Why do we take this route? Abandoning the Boltzmann-Stahl statistics, as I said. Why do we take this pathway and not this pathway? Why don't we try to compute 3D LTE synthetic spectra? Well, the reason is that if your elements and most diagnostic lines come from neutral minority species in the stellar atmospheres, and they have a non-LTE sensitivity. That means that if you compute a 3D LTE synthetic spectrum, it gives you actually worse results because especially at low metallicities, the 3D models have a steeper temperature stratification that boosts the non-LTE effects. So in a 3D model, it's even more important that the non-LTE effects are considered. As I said, for GALAH DR3, we are here for 12 elements and 600,000 stars, and 3D non-LTE has been done for up to 10 elements for the sun and some stars. There's also been grids made for 4 elements, but with very simple atomic structures. And if you want to see how these different assumptions can actually affect abundance measurements, these are not GALAH data, but it's very illustrative, I think. It's a study by Anish Amarsi on the carbon to oxygen ratio as a function of oxygen in the galaxy. And sorry, this is a halo sample. You can see that you infer a certain line slope with a traditional modeling, and that line slope is confirmed in LTE, in 3D. And there's actually almost no difference here. However, in 1D non-LTE, you get the opposite trend, and that trend is even steeper in non-LTE. So in this case, just wanted to stress the point again that it's better to take this route than this route if we want to land at the sort of ultimate answer, and that of course has implications for the origin of these species. For the GALAH data, you can see the impact of a non-LTE analysis here. I will flip back and forth between the LTE and non-LTE trends. This is a subset of about 50,000 stars where we analyzed all of them in both ways, so you can see how it actually affects things. You have sodium, magnesium, potassium, and manganese here. And overplotted is a chemical evolution model of the galaxy from Kobayashi et al. In blue. And then you have the dwarf and giant mean trends as well in solid and dashed lines that ideally should coincide, or we should at least have an explanation as to why they don't. So when I switch now to non-LTE, you see that the mean trend becomes more red, becomes more well defined. So the scatter around the mean is reduced. They also change slope. Oh, sorry. This is most obvious for potassium, which really has huge non-LTE effects. So and this is still rather well-behaved stars. I mean, it's predominantly solar metallicity stars that don't have enormous non-LTE effects, but you can still see that it strongly impacts our results. Right. So to finish off, I want to mention this paper here by my former PhD student Shudong. And we go back to all these lithium measurements that I showed you earlier. The title of the paper is A New Constraint on Cosmological Lithium and Galactic Lithium Evolution from Warm Dwarf Stars. So this HR diagram you saw previously, it's just showing you all the GALAH targets in terms of their number density. However, we can also do a different exercise. We color code each of the stars with its lithium abundance. And I do this keeping only now the detections. We only have detections for about 1/4 of the sample. But then you'll see something like this. Right, so here the colors now correspond from red to green to blue to increasing lithium abundance. So it's really fascinating, I think, that you can really see stellar evolution happening at the surface of the stars, and it's mirrored through their lithium abundance. So the main gradient here from high to low, that simply comes from the extent of the convective envelopes in these stars. That the larger the convective envelope, the excuse me, the more likely that lithium is drained into deeper regions inside the star, where it can be destroyed by proton capture reactions. However, you also see some interesting deviations from that trend. You can see here that there's a gap. And that I'll show you in the next slide. We'll zoom in on this region, but that is what we believe to be the lithium dip as it evolves. The so-called lithium dip is a feature that has been seen in clusters before, in open clusters, like the Hyades most famously. It's simply a region around 6,600 Kelvin where where lithium vanishes really early. So the interior of the structure of the star and the mixing processes induced by rotation and meridional circulation is such that it strongly favors lithium depletion. And what we see here is simply the evolution of those stars. So the reason why it's empty is because we can't measure lithium in these stars there. We can't detect it. And then we also have and this is interesting because when we talk about galactic chemical evolution of lithium, and especially the findings of a plateau towards lower metallicities that is famously dubbed the split plateau, those studies have focused on stars over here in this little box here, basically, where to the right of the lithium dip. But with GALAH survey, we can now, for the first time, we have enough measurements on the other side. So we can do the same exercise in trying to trace the chemical evolution of lithium using stars that possibly have retained even more lithium than the stars on the other side. Also, you can see how the red clump is really glowing here, telling us something about lithium production in stars. And there are 3 GALAH consortium papers on lithium. The one I'll show you in the next slides concerning the turnoff and the early subgiant branch. And we have another paper on the red clump explaining what's going on here. And there's also one comparing accreted and in situ, the in situ component of the galactic halo in terms of the lithium abundances. But yes, so here's a zoom in on the turnoff region, and you see here 2 panels. One with where we can't detect lithium, so these are non-detections, and you see this sort of a blob here that we call the dip. Corresponding to this emptiness here in the lithium detection panel. And we've made 2 naive triangles simply around these, to the left and to the right of this blob, to compare how lithium acts as a function of metallicity. But before we do that, I will show you the same thing, but just overplot stellar evolutionary tracks so that you can see what's going on. So here we have both detections and non-detections mixed. So the non-detections have here been color-coded with the upper limit to the lithium abundance, while the detections, of course, have the lithium abundance that we measured. And the same triangles as you saw on the previous plot are here as well. And then stellar tracks are crossing crossing here the regions as expected. So this is just a confirmation that it is the lithium dip we're seeing, but the stars are evolving, they're moving towards the subgiant branch. And so at solar metallicity, you have a 1.3 solar mass star moving across this region. If you go to slightly higher metallicities, you need to have a higher mass star to go through the same region. At lower metallicities, you lower the mass. However, ideally, we would like to go down to very low metallicities, but we're running out of data, and the stars that are supposed to be over here, they have long since evolved off, and they do not appear in these locations anymore. But yeah, we can see at least sort of what's happening down to of the order minus 1, minus 0.75 or so in metallicity. So the panel here is just showing you all the stars, and you can already see from this panel here that the stars in the blue triangle have higher lithium abundances on average than the cool stars. But if we take all the stars here in the red triangle and plot lithium abundance as a function of metallicity, and do the same with the blue, you see this. Right, so starting with the red triangle and the corresponding then to the red blob here, you can see that we recover the split plateau towards lower metallicity of the order of 2.2 or so. And the offset here with the predicted abundance from standard Big Bang nucleosynthesis, that is the famous so-called cosmological lithium problem. We don't know what's happening, what happened to that lithium, or is standard Big Bang nucleosynthesis wrong? However, if you compare that now to the blue stars and the blue density plots here, you can see that actually it is they are exactly 0.4x the amount missing, the amount that needs to be missing, that is the exact offset between these two groups. And the offset is very steady over a large range in metallicity. And at the lowest point, the average abundances in these stars, so the warm, most metal poor stars in this group here, actually have abundances that do reflect, that agree well with standard Big Bang nucleosynthesis. So it's not that far-fetched to believe, even though we haven't worked out all the details, but we are speculating that these stars may in fact have retained standard Big Bang lithium over the years. So they were born in environments where galactic production had not yet set in. That comes later, here at about minus 0.75 or so. And they're also stable. They're also much more stable than the cooler stars, so they do not destroy as much lithium. But you know, we need to do much more detailed comparison to the two galactic chemical evolution models and to stellar models to really reassure ourselves that this is what's going on. But it is a very interesting discovery, we think. So yeah, just iterating that point, the most metal-poor stars may have retained cosmological lithium. There are a large number of caveats, as with all things. Here we're really running into too close to the detection limit, which is temperature dependent. So we have to really visually look at everything to make sure that we're actually measuring the line itself and not something else. And there are dependencies that we haven't had time to look at yet, such as exactly how, I mean, the lithium abundance in the atmosphere depends on many things, not just age and mass, but metallicity and stellar rotation, for example. It is the big question is, of course, can such metal-poor regions survive without being enriched in lithium for a long time before these stars were born, because they are hot, so they're not old. They're not 10 gigayears old. They're a few gigayears old only. And that would require an inhomogeneous model, a chemical evolution model of the galaxy to really answer. And we need to get a better understanding of how lithium really is produced. Right, and then there's post-main sequence evolution of lithium potentially interfering with this naive picture. Okay, so to finish off, I would like to just mention what we're working on at the moment, and that is what I hope to do with my group in Stockholm. We are extending the library that we have of non-LT atomic models. We are working on the iron peak elements in particular now. So that we can convert them to green, meaning we have a reliable atomic model with good transition probabilities, both radiative and collisional, and that work is done in close collaboration, of course, with atomic physicists. We're also in the process to extend the existing grid that we have of 3D hydrodynamical model atmospheres. You can see the blue points here mark the existing models. However, even though the tracks here might disagree with you, they more metal-poor tracks, for example, really follow the edges here, and we need more models at the boundaries of the existing grid to be able to use it for quantitative spectroscopy. And what we definitely need are these models, because interpolating spectra over 500 Kelvin just gives too much room for error. Also, when the two other dimensions, surface gravity and metallicity, come in. So, as I said, if we want to use 3D atmosphere more routinely in abundance and spectroscopic work in general, then we need more atmospheric models. And we are expecting a whole lot more data to be coming in very soon. As I said, GALAH is continuing observations, but there are also other surveys going on. We are involved in the WEAVE and the foremost surveys that are going to deliver 4 million versus 16 million stars in just in the next few years, really, in the next decade. So that means that we probably have to abandon these 2-hour per star analysis techniques and really have to work out something better. And I will not ask you to read every single box here. I'm just saying that the traditional techniques do survive also in the foremost data flow, in the sense that we are hoping to integrate the Python version of SME for at least for training set analysis in the galactic pipeline that will process all the 16 million stars that that foremost will observe. So to summarize this talk, GALAH's third data release is coming up in a few hours, and it will deliver parameters, abundances, and reduced spectra for 0.6 million stars, which is a milestone in this in the dawn of this era. I hope I convinced you that analysis techniques have improved, and they improve rapidly, but we need to be aware of the many different flags and all the long list of caveats that exist in order to interpret this data in the best way. And much work is still to be done in order for the field to transition to full 3D non-LTE, but we've done a good job to have at least systematic errors of LTE under control in 1D. So with that, I'd like to thank you for your attention. Happy to take questions.
Great, thanks, Karin. That was really interesting talk. Thank you very much for that. I have to stop the video. Okay, I will stop the video.